are going to get back to what we were discussing. If you remember, we were talking about memory consistency models in the context of multiprocessing. And some of those also apply to databases because there also same issues come. There is concurrency and there are multiple transactions in that context associated with the same piece of data. And ultimately, there has to be some expectation that the programmer makes from how the data gets modified. And we are going to limit ourselves to multiprocessing, where you're not talking about large transactions, but small accesses, which is read, write into some location that may be directly a shared memory location or something that appears like a shared memory, something that is accessible, a memory location that is remote. We discussed strict consistency, where you basically have everything appear instantly. There is a global clock, you make a read, and instantly the read returns the thing that's read. You make a write, and instantly it's written. Okay. In sequential consistency, we do recognize that things will not happen instantly. You will have something that begins, and sometime later it will end. So start of read will be when you make that request, and end of the read will be when the data comes back. Similarly, start of a write is when you make that request, end of the write is when everybody sees that new data, right? Beyond that, past that point. And so this notion of sequential consistency says that there are these read and write accesses to shared memory. They can be ordered as if they were being run in a sequential environment, right? Meaning that all the different reads and writes of different multiprocessors have to be put in one linear order. In this order, so this order must be what the program ultimately saw. It must be consistent with the program, overall program, the multiprocessor parallel program saw, and it must be consistent with each processor's order. Okay, so if a processor said read then write, then that's what the overall global order contains. There was also a variant, not of sequential consistency, but mostly of strict consistency, which was linearizable, where it was not perfectly instantaneous. It said that you say read, and read happens at that exact moment. There's some leeway, some laxity, and says, I said read here, my response came back there, and sometime during that period, it is as if that read happened instantly at that spot between my sending of the request and getting the response back. Similarly for the write. Okay. There is a notion of global clock, because we are saying here is a read happening at this time, here is a read happening at this time, and then they are consistently ordered with respect to each other if they are not overlapping. Okay. And even if they are overlapping, there will be some order, but that order is not fixed because this read can be atomized at any point during that process, during the sending the request and getting the response back process. Okay. All right. So I also mentioned that sequential consistency is somewhat harder to implement. Right? It's already somewhat looser than strict consistency. And the reasons that it is hard to implement is essentially that it is saying that everything that is in the program order must be maintained. Right? If the program said write, then read, then in your final response, every other processor must see that write, then that read. Okay, and that means that there is no reordering allowed. Now, compiler cannot reorder, and transactions to memory, read and write transactions to memory, cannot pass each other. Okay, and it's actually quite easy for them to pass. In fact, most architectures allow them to pass. And that's why, and the reason that they allow them to pass is to keep things efficient, to keep it not every operation stuck behind a long operation like a read, like a write, which will typically take longer than a read. So here is an example. You've got two processors. I've marked them T0 and T1 because that in our terminology we are calling them threads. They may be running on the same processor. They may be running on multiple processors, different cores on the same processor, whatever. So there are these threads that are that have local L1 cache. Okay, and L1 cache is backed up by an L2 cache. L1 cache is write through, L2 cache is write back, and then there is memory. Okay, and the data when you write something to the memory, it's going to check if it is in the cache, right? And it is write through, so it has that memory write has to go through all the way to the main memory. Okay, so that memory write transaction will get queued into a buffer between L1 and L2.
L1 write through doesn't mean an L2 is write back, so doesn't stop at L2.
In this case, it will stop at L2, but L2 write through will also have a similar issue.
Write back means?
Write through means whatever you write has to also be written into the backstore, into whatever this thing is representing. And write back is lazy. I'm going to write it here. Later on, I can read directly from here, but the write back will happen when this needs to be evicted or some other condition becomes true. All right, so you when there is a single processor, then there is no problem, because what's going to happen is the writes will get queued in the memory in this buffer, and it's possible that you read something. Can that read effectively finish before that write? Even in one processor it can. So there are reads and writes that the processor is issuing, and there is an L1 cache. If you write, then the write transaction has to go through. Right? If you read, and if it is in L1 cache, then it's going to get returned. Otherwise, if it doesn't get returned, then this read is waiting for that write. Okay, but what's going to happen in a single processor? It is possible that you get read returned from cache, and the write is still not done. It's in the queue. However, if it is a non-conflicting read, meaning that you're reading something else, you have written something else, then you don't care. If it is a conflicting read, you're reading the same thing that you have written, your cache is up to date. You've written it in L1 before sending it down. Okay, so that reordering can happen, is allowed, but nobody cares about it. Now we are saying, because every other processor must also see which order you were issuing transactions in, I can't have you see a different order and other processors see a different order. As a result of which, the read cannot bypass the write, even if it is unrelated. So you wrote to one variable, it is stuck in the queue, then you read something else that is sitting merrily in the cache, but you can't return it, because otherwise other people will see that the read happened later, but you will see that the read happened first. Read came back first because you read from the cache.
How will the other people see if it is right in my cache, my local cache?
But the read transaction will be ultimately serialized, right? It has to be put somewhere. And so if other people don't see that your read happened first, then they may behave as if your read happened later. As a result of which you cannot put this one wants read here, the other people want read there, and so there is no way to serialize. And so in maintaining sequential consistency, essentially every reordering has to be killed. Everything has to be in order, and not just in order, but you have to wait for the previous transaction to finish before this transaction can proceed.
The beginning order and the finishing order should match.
Should match, right? As a result of which, you are essentially paying for that latency every single time. There is no benefit of cache, unless you're only doing reads, in which case it's perfectly fine. And this skew can get even worse if this is not just going to the same shared memory off to a common bus which keeps things ordered, but on to a network where some shared memory is on this machine, some shared memory is on, or some accessed memory is on this machine, some on that machine, some on the third machine. So it only gets worse. Okay, so and latencies get worse, which means everybody has to pay the price for every latency. Okay. So essentially, in order to implement sequential consistency, we are going to have to maintain this ordering, and the only way you guarantee this is saying don't issue the next until the previous one is completed. And completed means visible to everybody. Everybody thinks it has completed. Okay, so if you're sending it to a remote location, you must get an ACK back that it has completed before you can know that it has completed, and that ACK is being sent to everybody. So there are variants. One is you allow things to proceed out of order, but you keep detecting if later on there is somebody else that might see it in the wrong order. Okay, and these get quite complicated quite quickly, where you allow it to get out of order, but keep track of what out of order things have happened. Okay, and at a point where it actually is going to make a problem that this fellow wants to do it in AB order and some other processor wants to do it in BA order, it's going to stop that transaction at that moment. Okay, so it's always looking for an actual conflict to happen rather than that an assumption that a conflict might happen. Somebody might see it in the other order.
This is at runtime.
This is at runtime. It typically needs some hardware support for it. So if the hardware doesn't have any support for it, then on software basis you can hardly do this. There are other weaker models that we will look at least a few of them, where you say, I'm not going to worry about this global strict, not the strict consistency, but global sequential consistency, where the exact order for every transaction has to be maintained. Okay, and there are situations in which you wouldn't care, especially if you are maintaining some order in a semantic way. Right? Here is an example where you've got thread 1 and thread 2. They have a lock, and thread 1 says, here is something in data 1, here is something in data 2, and now I'm going to unlock something so that somebody else may lock this region. So there's a critical region. I lock, set the values, unlock. Only then can somebody get that lock, fetch those values that I wrote, and then do something with it. In this case, those can be reordered, right? Data 1, data 2 can be written in any order. They can be read in any order. Because semantically, I have ensured that doesn't matter. So there are these kinds of generalizations that are made, and one of them, or simplifications rather, that are made, and one of them is this weak consistency model that we have seen before in the context of OpenMP. But there are some in between weak and sequential.
What is the difference? Why don't I reorder the log statement with the data statement?
You might, this is saying that if you keep the log there, you can reorder those data and nobody will care. So here is an example of something where even if you violate sequential consistency, the program will be, okay, so it's not, sequential consistency may be an overkill most of the time. You don't always need sequential consistency. And as a matter of fact, that's why essentially no multiprocessor environment really guarantees sequential consistency. So there is this notion of causal consistency, which says that let's relate operations that may depend on each other. So let's not say every operation, every access that I make has to be ordered in the order I specified them, I made them in. You only do this for things that depend on each other. Okay? So there is this notion of causality, which says if I write something, then this write has to be ordered after all the other accesses. Okay, so write is somehow special. Why after all accesses?
After all access currently with the process.
So we are still going to linearize the reads and writes. Right? In global sequential consistency, we said that must respect my order. Now I am saying that need not respect all of my order. But these are two orders it must respect. If I have a write, that write must be ordered after everything that came before it. Okay? Everything, because whatever I have read is in some sense the state that determines this write. This written value may be a function of everything I have read. So anything conflicting or non-conflicting, anything I have read before or written, right? Because if I write in the wrong order, then people will see them in the wrong order. Anything that has happened before a write has to happen before in the final order, in the final sequentializing order. But the read is only ordered with respect to its conflicting write. Yeah, if I read some variable x, and you have written that variable x before, or rather I have written that variable x before, then that written has to come before that read.
Does the first statement not imply the second?
No, first statement only says write has to be ordered after everything before it, not about what comes after it. This can reorder itself with respect to it, except if it conflicts. So write of something, write of x, read of y, can have read go there, and I don't care. Okay. And then of course causality is transitive. If I have to come before you and you have to come before somebody else, then I better come before somebody else. And only these two kinds of relationships of every single program needs to be maintained. Okay. So
That write can be in any other processors.
No. So eventually our goal is to create an order, global order, which respects every processor's order, right? In this case, it doesn't have to respect all the orders of every processor, only the causal orders. Okay, so it must respect the causal orders of processor 0, causal orders of processor 1, and so on.
Not inter-processor orders.
So that interprocessor order is...
Different location might be written and read by two processors.
Yeah, so it's the same thing as we did in sequential consistency, right? If my value was read by that person, then the final order must put that read after my write. Right? So final order must be equivalent to some sequential order. Right? Different sequential orders will give you different results of the program. but they're all consistent. Right? What result you want is up to the program, right? If you want some specific reordering, you've got to synchronize. But as far as the memory contract is concerned, it says that as long as this order can be given so that everybody sees a consistent order, memory is done. If you want some more semantics on top of it, then that's program's responsibility.
So how can I read and write conflict if it's talking about a single process?
How can read and write conflict? If you're doing the same variable. Same variable, that's the definition.
Same variable on a process.
Yes. So if this processor reads X and writes X, right?
But it would be, it's not conflicting, right? Because if the program says read X and then write X, so according to the first condition, read should come before write.
Yes.
And so you are saying that these are two consecutive statements, one is write and then read.
Not consecutive necessarily. It's with respect to every other. So for a write, it says that all the accesses before it have to be kept before. And for a read, it says that all the accesses before it, which are writes, and to the same variable, have to be kept before. A bit weaker version, which is called the processor consistency. And this is something that actually many hardware support, including Intel. Or it doesn't mean that they provide. It's something that can be supported when you put it on multiple machines. And in the processor consistency, essentially, you don't relate all kinds of causal accesses. It simply says that the memory accesses that are writes from a given processor must be put in the same order. Okay, so if processor A writes A, B, C, D, then everybody must see A happen before B, before C, before D.
Reads are immaterial.
Reads are immaterial. Okay. There is, so just that by itself is what is called FIFO consistency. Okay, processor consistency is a little bit stronger than that, where the writes for a given variable X must be seen in the same order everywhere. Okay, so if this fellow writes X, or let's say pick a variable X, all the writes to variable X must be ordered consistently everywhere. Right? Consistently meaning ordered with respect to processor A's writes, processor B's writes, processor C's writes, and processor D's writes. Okay. If you remove that, when you simply say all the writes happen in the order they were issued, then that becomes what is known as FIFO consistency. It went away, but it's coming back. FIFO consistency. Okay, you remove that restriction. And FIFO consistency is relatively easy to implement, where you remove even the second restriction. Basically, say writes are pipelined. Right? In fact, that's why it's also sometimes called pipelined consistency, the FIFO consistency. And the name FIFO also suggests basically the same thing. Right? That when I first write that a processor makes will get affected or will complete before the second write that the processor makes. Right? So writes along the way can't cross each other. That's all. Okay. So the relationship with reads has gone away, as a result of which this is weaker. And processor, in fact, has not much more to do, right? It says all the writes are pipeline, writes can't overtake each other, reads can come back from cache early, and it's still fine. Okay? It's now the more lax the consistency model becomes, harder it becomes for the program or programmer to ensure that your semantics is maintained. Right? That means you have to make sure that everything is synchronized. Okay?
Can we have an example for the thing that keep condition has been relaxed and still we are having the same sequence of writes? Like if I have 4 processors and there are some sequence of writes among all of them. So in any case, if I am saying for both of these models,
Both meaning processor and FIFO.
I'm saying that my writes should be ordered. So even if it is interprocessor, if I'm saying my writes should be ordered, that means for either of the one it's going to be same.
No. The writes that were issued from the same processor are, so you take the subset of writes issued by processor. All the accesses come in the form of, this is a write to variable X by processor Y, right? So writes have two kind of subscripts associated with it, right? So one is with the processor, the other is with the variable.
And the second one, I'm not restricting interprocessor.
The variable, right? Only the processor has to be consistent. And finally, the weak consistency model, where there is an explicit, there is a special type of access that is called the synchronization access, right? And it says that if you want your accesses to be synchronized, to be consistent, then you make this special type of access. You don't simply say read X, you say read consistent X of something of that sort. And the read consistent and the write consistent will be synchronized with respect to each other, will be sequentially consistent with respect to each other. All the other reads, they can happen in whichever order. Okay? And that is in fact what OpenMP does, right?
But is this related to the, consistency read and the normal read and write? I mean, don't they?
So it's like normal read and write are not memory accesses at all. When you make these special consistent read and consistent write accesses, only those need to be serialized.
Right. Others can happen in the.
Others can be seen by different processors in different order, doesn't matter.
But there's no relation between these two?
No.
So the programmer specifies that this read is going to be consistent.
No, there's some semantics that the programmer wants, right? It says that this read must happen before that read, and then it's programmer's responsibility to either call it synchronous, right? Call it synchronized read, or make a lock. Right? You do the read, then synchronize whatever barrier, whatever your synchronization method may be, and then do the other read. Okay, and so the special type of synchronization access for OpenMP is the flushed access. Right? When you say flush something, that means the reads and writes to that variable are being synchronized. And of course, there are some things that are implicitly flushed, right? Barrier variables, flushes that happen at the end of parallel construct, for example. But either implicit or explicit, each access is either a flush access or a non-flush access, meaning it's either a synchronization access or a non-synchronization access. And only the flush accesses will get consistent with respect to each other. It's even weaker than weak consistency, because not flush of A here and flush of B here will be made consistent. These two flushes will be made consistent if this says flush AB and this says flush AB. Right? If these two flushes have an intersection, then they will be made consistent with respect to each other. Otherwise, it's like non-synchronized access. Okay. And so,
Second point, it says that before regular rewrite performed, The next one. Say the all previous ordinary read-write accesses must be performed. The second point under other accesses are consistent. Saying it before and
So yeah, so this is within a processor, it has to be consistent. Right? Within a processor, you read something and then you do a flush read. Then that processor has to see that this happened before that happened.
Only the flush read.
No. Within a processor, it's like sequential environment. Right? So automatically anything that processor sees has to be in that order. But among the processors, where you are serializing all the accesses, these processors, the non-flush or non-synchronized accesses don't exist. They don't have to be put in a specific place among the list of flush. Okay.
So they said that before a synchronization access is allowed to perform with respect to any other processor, all previous ordinary read-write access must be performed.
For that processor. Okay, so here is a quick summary. There is strict, which is essentially impossible, right? Because you say that it becomes instantaneous. You make the read call, and that time that you made the read call is when it happens. So everything is deterministic. In sequential consistency, it is equivalent to some sequential set of operations. And if you want your sequential set of operations, it's your business. It's equivalent to some sequential set of operations, but it has to be consistent for all operations of each processor. Okay? And causal says not all operations of each processor, only related operations of each processor. This special causal relationship is to be respected. And then that related definition is weakened further by saying that in processor consistency, specific writes and reads are related, and in weak consistency, only the flushed or synchronized reads and writes are related. Okay. Any question?
So what do atoms or laptops have?
The implementation of Intel's architecture does processor consistency. Okay, but you have to remember that that's an almost irrelevant question when you are a programmer, because you're not directly calling processor instructions, right? There are fence instructions that it uses to make sure that these are consistent, that the accesses are consistent. But between the hardware and you is sitting an OpenMP layer, if you're using it, a compiler layer. So there are all these layers together provide you some guarantee of one or the other consistency.
So they shield you from this.
Sorry?
There's consistency not happening below, they shield you from it. I mean, they try to implement some sort of consistency in this way.
So, for example, if you're using OpenMP, right, it says I'm going to guarantee to you this special type of weak consistency. Right? So it's the entire environment which provides that guarantee, that contract. So whatever the underlying hardware supports is somewhat irrelevant.
It is irrespective of.
But Intel hardware does support if you want to build a new OpenMP which provides processor consistency, you can do that.
So there was some order when we did that ECRW and where the power increases, then we can implement it in constant time. So is there some order in this one also, so that we can implement one using the other, provide some hardware, gives you some model, then implement another one?
Yes, there is no results on their relationship in terms of timing, right? But one is clearly stronger than the other, right? Where you're saying that thing is being relaxed in this. Right? So this is strictly more strict than this, because those have to be ordered like you said, but this additional ordering has to be maintained because I want some more constraints. Okay, so there is a strict precedence.
It cannot be implemented using the stricter one. If there is stricter underlying thing, it cannot implement a weaker model.
That is a harder thing to say, right? Because weaker model is not, that's not all of the model. That's part of it, right? Meaning that there may be features like locking, test and set instructions, other things that you can use to encapsulate the accesses to provide a stronger consistency model. For example, if you wanted sequential consistency,
Provide a stronger consistency model than what is there.
It can be.
But a weaker consistency. There is a stronger one at the bottom. Can we implement a weaker one at the top?
Obviously,
Of course,
it's a subset.
a weaker one is automatically implemented when you implemented the stronger one. But to implement the stronger one, you have to pay some price. And it can be done, but you may have to lock, you may have to synchronize, you may have to do some special.
The things that programmer has to do are now inbuilt in the.
Exactly.
No, but even with weak, you have using a weak thing, you can make a straight one because you have a notion of a law.
Yes, absolutely. That's
In that sense, they are equivalent.
exactly not equivalent, but they're just the different environments. Right? If with the weak thing you have some other features, they together can implement something strong.
And you have those features.
Yes, yes. All right. So now we are going to we've talked about the consistency, and to some extent we have talked about the fact that one is faster to implement than the other. We'll talk about general programming performance issues for shared memory or memory that is distributed across multiple processors. And then get on to some of the issues in designing parallel programs. Okay. So one of the things that if you are aware of and if you account for in your program, you can make a significant difference to its performance, which is called false share. Okay? Meaning that everything we have said so far, read X is conflicting with this read X, in reality gets mapped to read of a cache line where X belongs is conflicting with a read of a cache line where Y belongs. Right? Because entire cache lines are flushed at a time. So if you have one element that you've written into the cache line, that entire cache line is going to get flushed. Okay? Or if you're reading one element from a cache line that is not in cache, or one element that is not in cache, then that entire cache line will be fetched. Right? So this is called false sharing. I said I have variable X and a variable Y, and I've written variable X and I have read variable Y, and I assume there is no conflict. Okay? But internally there will be, as a result of which it has to maintain the sequential or whatever the consistency it's providing. But the fact that it had to write something into the main memory when you only wanted to write one part of it means that there is more synchronization happening than you thought, right? Or you expected. So when that happens, when you have two variables in the same cache line, it's called false sharing, versus the same variable. When I'm reading some variable here and reading that variable or writing to that variable again later. There aren't I can give you some heuristic type solutions that are listed on the slide, but there isn't really a good way to detect or eliminate or a systematic way, I should say, to make sure that you don't or reduce in any sense false sharing. Okay. But mostly what you can do is allocate things in a certain fashion. This will become very clear and important rather when we start talking about CUDA, where we are very aware of the memory hierarchy and the memory structure. Let me give you an example. Here is a struct which has variable A, field A, and field B. Okay, and I've got an array of this struct. And somewhere I say, go sum up all the values, all the A values in the struct. Okay, so for I equal to 0 to n, sum plus is equal to f dot x. And then a little while later, I go do something to all the y fields. Okay, I'm adding in this case sum to each y member.
A will be JB. X dot A should be better than that.
Oh, I see. Okay, sorry. Yes, let me
Represent X in
fix this. When you were going through the first loop, you were jumping all the B's, right? Because A and B are contiguous. The entire structure of memory is A, B, A, B, A, B, A, B. Okay. So this is what is also known as an array of structs. Okay. An alternative might have been what is called a struct of arrays, right? Structure of arrays, where you say, I've got an array which is A, and an array which is B, and a struct which is just these two members. An array of A and an array of B. Okay. So in this case, you were paying the price for accessing B in the first loop, and you are paying the price for accessing A in the second loop, because in all likelihood that A and B belong to the same cache line. So whenever A is being fetched, B is being fetched. Okay. In this case, if this is what you had to do, you could eliminate this false sharing by using, in this case again, a struct of arrays. Right? All the A's are together, all the B's come later. So now if you're reading the variables in A, the members in the array A, then you're getting good utilization of the cache line. Right? You read a few members of A, process them, you read a few members of A again, process them, and so on.
That's right. Then there's a battle, right? I mean, how good the code is, how easy is it to program, and how efficient it is.
That battle is always there, and parallel programming only makes it even worse. And the truth is that you can imagine, and some of it is actually done also, a compiler figuring this out, right? And just reordering A and B. It's actually very hard. Research goes on in how to do that consistently without introducing error in all contexts. Cannot be done as of today.
So what reordering the array of structs is converted to struct of arrays.
I don't know of any that does that. That would be a significant change. Reordering of accesses, for example, right? So if you have a loop, two-dimensional array that goes for I equal to 0 to n, j is equal to 0 to m, that can be reordered in some contexts. That kind of thing is possible and done. Yeah, so outer loop is going through rows, inner loop is going through columns. You translate them. You say outer loop goes through columns, inner loop goes through rows, in order to make the cache behavior better, meaning false sharing reduced. Okay. Some other high-level performance considerations. Clearly, you want to keep critical regions short, if especially you have lots of them, meaning that whenever somebody is in critical region, it is probably stopping somebody else from coming there, and that somebody else is sitting waiting, doing nothing. Okay, so you should keep them as short as you can.
But this does not come from any of the discussion that you just had.
These are just other performance considerations. That's why it's aptly titled. And in fact, we'll go through a few, call them tips or whatever, through this discussion of parallel programming. that are more from experience than from anything else. Again, all kinds of synchronization. So the critical region is one example. Essentially, you want to limit your synchronization as much as possible, and we'll talk about it in more detail soon enough. But you can essentially batch synchronizations. You can say, instead of saying, do this and make sure everybody has done that, and do this and make sure everybody has done that, you can say, let's do this much and make sure everybody has done that much. Right? So you are basically reducing the synchronization per computation overall. Okay? And that's ultimately the goal. You can't eliminate synchronization, but for each synchronization, you want to make the best use of it, take the most advantage out of that synchronization. We were just talking about the loops. You can say, for example, in pair for, it's possible that outside loop has a lot of communication, but inside loop is all parallel. There's no, every iteration of the loop working on independent unit of data. You can reorder those loops so that now outside loops have independent units of work, and each work is now lots of dependent things that can be done sequentially on each processor. Okay. And then finally, use enough threads. Again, nobody knows what that number is. It depends on the architecture, it depends on your program, it depends on the overhead of synchronization and communication versus the computation time. But again, I think I had mentioned that you essentially use the rule of the thumb that you have at least 4 to 5 times active threads at any given time, so that you can hide latencies. If they are all pure compute jobs where you're doing nothing but taking two values in the register and doing some operation on them, which is quite rare, then you don't need too many threads. But as soon as you start to do communications mixed with computation, memory accesses mixed with computation, you want to have 4, 5, maybe even 10 times the number of threads as you have number of processors. Okay. Sometimes, so I said active threads, right? 4 to 5 times are the active threads. Sometimes when you break your tasks down, you may actually have logically many more threads. Let's say I've got work here divided among 1,000 threads. I'm having these 10 threads, and these 10 threads will do 10 of those, 10 of the 1,000 work, and anybody who gets done can do some more. Okay, that's another way of organizing your computation. We'll talk a little bit more of that. Here is one example of how you might want to shorten the critical region. What does this do? You in the critical region, you're adding something into this shared variable, which is hopefully being, or as presumably being added to or operated upon by somebody else who also wants to be in the same critical region, who's protected by critical. So you say in this critical region, area is going to get added with 4 over 1 plus x squared. Right? Seems like a small enough critical region, but it's not the smallest. You only need access to area inside the critical region. Why are you doing all this other computation? You can move all of that outside and only assign the variable. And of course, if you have other features like atomic operations, you might use that. Right? So that's still, it eventually it amounts to having a critical region. Atomic operations are equivalent to critical regions, but then it's really narrowed down to when that write is going to happen. So that critical region has become even further bound in terms of the range of clocks where that is active. Okay.
This is, I don't know if reduction will be parallel or
Yeah. In fact, I did reduction here. I was actually meaning to do atomic, where you atomically add to the area. Yeah, reduction is another example where you simply eliminate the critical region, but then there is some baggage, as you pointed out. It may not be being done in parallel. You have to note that in this example, it was anyway not being done in parallel, because everybody was waiting to add its value. And so even if reduction is not being done in parallel, at least you've got rid of everybody waiting for that long period.
So, a critical section is something that I cannot avoid, right? I mean, over here it is avoidable.
Yes, over here is avoidable, but you generally cannot avoid.
So, it will make sense to club all the critical section operations together into a large block rather than have them spread out.
Not always, right? So there is this trade-off that you have to make between how often you have to synchronize versus if you have to wait for that long to synchronize, is somebody else waiting much earlier for the same synchronization and hence idle for a long period?
When you said that atomic is synchronization only for a very small, so I was questioning that. So is it helpful that the code inside it is very small because the synchronization overhead is before and after the...
It depends, right? If you can club two synchronization things, it can help sometimes, right? But you don't club doing a lot of unrelated work in between. You typically club if all of this work has been related to synchronization, meaning that if you can say I'm taking these 10 synchronization steps and turning it into one, where all 10 were needed. Yeah. That's not the case here. Right? That can help. That's the discussion we were just having. That sometimes you want to say, instead of do this, synchronize, you say do all of this and then synchronize. Right? That does make sense. But you still have to do enough useful work between the synchronizations. And then you can't simply club everything because people are proceeding at different speeds, and if you synchronize there, then the level of idleness across the system is potentially going to increase. Okay.
In the critical section, there is something about the name of the critical section. So, and we don't want to club those critical sections which are unrelated or have a different name. For example.
Yes. Because they will not, they are not contending with each other.
So when one thread is in one region, another one will do something.
Yes. Yeah. So if you club them, again there is inspection of the code needed to make sure that you're making the right decision. But typically you would expect that you don't want to club unrelated critical sections, because you're basically adding synchronization. Things that were not going to wait for that region are now going to wait for it. Right? Okay. And this work queue model, again, we'll come back to it. It is more of a how do you manage, especially when work gets dynamically generated. Right? Sometimes you say, I've got these 1,000 things to do. I've got these 5 processors to do them. Go do it. Right? At other times you say, I've got this one thing to do, but while doing that, I'll figure out what more is to be done. Right? And so work keeps getting generated dynamically. And especially in cases like that, work queue becomes very important, or useful rather, where you simply have some kind of a loop where you say, if there is some more work, let me take the next thing that's available to do, or that is ready to be done, and let me do that. Okay? And all the processors are doing the same thing. Of course, there is issues with synchronization. Right? You don't want 2 people to take the same work. You don't want some work to be not taken by anybody. So those things will automatically get done if the queue is a critical region. We'll look later whether the entire queue has to be a critical region, or you can again reduce that critical region to a very small instruction section, or probably eliminate it altogether. Here is more details on the same thing. I'll probably skip through this code. It's not really adding that much, especially because we are going to come back to this notion of work use. So review in the context only of memory. Right? So we've been talking about memory consistency, memory performance. We've talked a little bit about load balancing, or keeping people non-idle working. We'll focus on that side. How do you keep how do you distribute tasks? How do you design the tasks? How do you make processors take the next task and all that? But in the memory side, you've got to understand the consistency model. Right? And based on that model, you have to figure out what semantics you want and synchronize accesses where they are necessary. Okay? That's part of the programmer's job. Once you've done that, you have to look at where you can eliminate slowness by reducing false sharing, reducing critical region, and the like. Any questions on that? And I typically people would talk about computation parallelization, then if at all talk about memory. Okay, I have done the opposite on purpose because memory optimization is very often ignored and is an equal partner, if not in some contexts the more important partner in getting the maximum speed up when you're parallelizing. Okay, so the next thing we'll talk about is computation parallelization, but we'll stop here and we'll continue.